Stanford University. And well, I give you the floor to make your talk. Thank you very much.
Thank you very much. And thank you for the invitation. It's a great pleasure to be here. And also I'd like to thank the three wonderful talks given by my previous three speakers. That has laid a perfect sort of a background and before I begin this talk. And I learned a great deal from all of them. You know, I think from Paul, I realized that there's nothing more certain in solving any problem than the uncertainty. And it's so complex that it requires human-machine integration and interaction. That's a complex problem. And nothing is more complex when you mix psychology and physics. That's enormous complexity. I don't have to repeat it here. I'm glad that they have articulated it so well. And Patrick talked about the smart grid. And I'm humbled by the experience. And the smart grid is such a good idea. Why we have heard about this for over 20 years. It hasn't happened yet. And yes, I think the electric power grid is a wonderful complex system. It's a human accomplishment. I think in year 2000, when the National Academy of Engineering in the US tried to put together the the greatest engineering accomplishments of humanity over the century, the vast connection of the electric network was ranked at #1. And one cannot really wonder, I think when we look at this iPhone, cannot really but question that. Now in the 19th century, and this telecommunications and electric power were both actually ingenious sort of innovations. But if we look at who is more genius, Thomas Edison or Graham Bell? And if you invite Graham Bell back to today, give him this, he does not even know how to operate it. And if we invite Thomas Edison to the operating room, he said, this is wonderful. This is the system I actually put together, designed. And today we call this a smartphone, and we call the grid dumb grid. And who is smarter? And we are trapped. Oh yeah, it is quite an experience. I think it's wonderful here today. I think for the young folks, it's a wonderful time for you. I think this is the moment of change, and it's a great opportunity to look at the unsolved problems. I was actually moving in my career from more a research and academic environment to more an operating environment. I think the change, to me, let me share it with you, it's really a humbling experience of striking the balance between theory and practice. I remember that there was a story I learned not too long ago. That there was an island, a desolated volcanic island near the Nordic Pole area and to the west of North Pole, about several hundred miles. On that island, there was a weather station. No man was sort of manning that station, but outside of that, there is a post with a language. If you translate a Nordic language into English, it goes something like this. Theory and practice. Theory is when you know everything, but nothing works. And practice is when everything works, but no one understands why. At this station, the theory and practice are united. So nothing works. Nobody understands why. Okay, so I think here at PJM, I'm here to share with you my observations of some of the things that we are trying to do. We call it reform. There is a formal term called electricity price formation, and there is a senior task force. If you look at PJM's website, that is ranked high up among the top sort of cooperate priorities. You cannot miss it. It's out there if you are interested. And and many of the questions my previous speakers raised, we are still searching. I'll guarantee that not all the questions have been answered, and we are moving on. So here I'm not actually telling you that we have full answers. And here is the mathematical center. I use some mathematics. And in my view that here, if I understand the problem sufficiently well, I should be able to formulate that in mathematics. Now that's really the criteria that we're using to describe that problem in mathematical terms, just to show that that is a precise statement. And then what we hope, when we get an answer, get a solution, we can describe it in such a layman terms that we can describe to taxi drivers, can talk to your barbershop barber, or can explain that to your grandmother. In a way, she will not say that, oh, Hung-po, you don't understand, because it's so complicated. So with that, I'm glad that I have some background, between theory and practice, and I can sort of talk to people, not because I know better. I think I look to you, who are the experts. I call it genius, basically, in various fields as a front runner in your domain field. So I hope that to raise some of these experiences and observations so that we can get really an intellectual network to crack on this problem. I think that's shared among between US and Europe. Okay, with that, let me see here. The PJM, this is basically show the map is that I cannot show the world. I think the Europe, that map was a lot more impressive. And basically, I think our talks is like a telescope, and moving from telescope to microscope. And here is really my microscope. We look at very microly and look at only at the PJM. So now we claim that this is the largest market in the world with 165 peak load and serving 65 million people. And with 13 states, you then politically, when you serve 13 states, they all have jurisdictional independence. You know how hard it is to make any reform. So I think there are a lot of check and balances here. Only common sense actually can flow. So hopefully that we establish a common sense and with a common ground, and then hopefully here that we are talking about that potentially in economic terms we can move on the basis of Pareto improvement, and if not Pareto optimality. Okay. Now, as an introduction, I must say that number one here is for any reform, we actually have to answer the question. If we are going to put anything on the table for folks to do, what is the problem? Is that a problem for you, or is that a problem for me? What is the problem for me? Everyone will ask that question. Not me doesn't mean narrowly only my pocket. That's a big part of me. But everyone has a view of what the world ought to be and what PJM should do and what the market should be like. And they are all very intelligent beings. So I think I don't have to persuade you after you hear the first three speakers' talks. So I think in my humble opinion here, number one is that over 20 years, I will answer the question Patrick asked about ELMP. But I think here I'm not going to defend anything. I'm just stating facts, and then I will tell you what the big problem. I think I share with Patrick a lot of observations here. On the surface, you see, over 20 years, PJM has been a successful market. No one questioned about that. Now, that debate is basically done. And the competitive market is a good thing. Over the 20 years, if you look at fuel adjusted, energy prices have been declining. And at the same time, we have attracted 40 gigawatt of new investment, new entry. Well, that's a big test. And then 20 years ago, you cannot take that for granted. When the market actually initially just was implemented, and year one, it was a failure. And people forgot about that because PJM was trying to adopt a European uniform pricing scheme and so forth, and that created panic. And then the next year, when the LMP was first introduced, initially it was a rocky start. And at the beginning, the peak price in the summer, in May, in 2000, it went up to $7,500 per megawatt hour. And we have never seen that high ever since. We will not actually get there, but that was the price. PJM was not alone, and New England, I was with New England previously, and their price was $6,000, and then New York was $5,000, and California, you know the story, that actually collapsed during that period into 2000, and the price only went up to $400. Actually, that bankrupted the utility. So this cannot be really taken for granted. This is a very solid fact that no one would question that this market has produced a lot of good things, including the shale gas, competitive combined cycle, all this technological innovation among many things. And that is a good thing. So we're not talking about the problem. It's not there is a failure. Now, there's no crisis, and then everyone calms down. But in recent years, and a lot actually people who are actually inside the market and knows how the nitty-gritty details, how it works, begin actually to project into the future to see, okay, we have got all over this since the 2000 California crisis. Now we actually are good. Is that going to sustain and continue forever? Well, we'll see that in PJM's market, there is, as an introduction of this market, there's a big shift between coal and natural gas. And that big shift outside is, oh, that's wonderful. They all clap their hands. But wait, that transition is not over yet. And that big shift involves a lot of dollar changes between two different groups without any sort of big war or conflict. But that is not going to be, that transition is not over yet. And while this transition have also occurred elsewhere, everyone has a different sort of challenges. And but in PJM, we see some unique challenges. And here I would like actually to share with you some observations to see whether we are doing crazy things. Because I think, my take on this price formation is that even PJM's LMP was introduced during a crisis. To do any sort of regulatory reform or crisis, I've heard that, I think this Supreme Court Judge Stephen Breyer actually once said something, I quoted that, to have a regulatory reform on the pricing, well, it's maybe easier to train a regulator to design a rocket to be sent to the moon than to change the prices. Okay. Now, this is what we just took. This is not an exhaustive list. Now we see the uplift payment. That's a mysterious term. Market should actually be cleared and market clearing, but there are some other side payments. The side payments are inevitable, persistent. It's around $2 billion for over 10 years. And when the load increases, supposedly in theory, the price should go up. And when people want to buy more, you actually burn more, and the price should go up. And 20% of the time, price actually dropped. And this market should be so efficient that everyone wants to be pool scheduled, but 60% regularly of the energy and capacity, it's a self-scheduled. They don't want actually pool scheduled, but they want pool to dispatch them. And not there. And many CT units that submit inflexible bit parameters. CTs are very flexible. You can design a configuration that anyway, it depends on the money, of course. You can put in features that it's very easy to operate. But turns out that we have a large chunk of CTs that are not so easy to operate because they bid in and say, my minimum runtime 2 hours, and you cannot really take on me, get me up in the next 30 minutes. And the revenue has been shifted from energy market to a capacity market. And during the 2014 polar vortex, we see that a significant jump. That cold winter, and then we find that a lot of units are not really available. We need actually to provide additional incentives. And now with the energy efficiency, that is also part of the outcome of markets. And demand growth has been flattening, and the supply curve, because of more of this entry are one type of generators based on gas, so supply curve has been flattening. And we see that although the PJM renewables remains to be a very small portion, like 5% or so, but we anticipate in the future that is really the way to go. When we get there, the supply curve will be flat, zero. And with that, in that world, is this wholesale market, the energy pricing, still relevant? The price will be zero. Okay. So even though we are not there yet, we ask all these questions. And would this be a problem? Okay, no. Some folks may say, no, that's okay. Well, no, that's a long time in the future. So this is what I talked about. This is a large chunk of money. We're talking about real monies, billions of dollars. And then initially that capacity energy market was really taking nearly 100% of the revenue, and now it's about 70%. And then, okay, this is our sort of, based on all of this, we saw the flexibility is a problem, and so what is the problem? And then this is an economist's take, and fundamentally, and non-convexity was really on the last slide of Patrick's slide. I think that's wonderful. You set up stage for this. And let me say that engineers all see non-convexities, and economists not only see non-convexities, they call it two theorems called the fundamental theorems of welfare economics. Are these two? The reason that we use competitive market is that competitive equilibrium generally is considered efficient. That's one of the fundamental theorems. That's why we use market mechanism. And there are conditions. Some of the conditions, I call it price takers. That is very important. If the market is not competitive, it's not going to be efficient. And there is a well-known, I think I just assume that is, that I don't have to explain it here. In economics, with a finite number of players, the traders, it's well known, it's a theorem, no market can be fully efficient. There's always a residual market power somewhere. Okay, and it becomes, and the players, all the traders will become a price taker only in the limit when the number of players goes to infinity. And that's generally good enough for the marginal cost pricing principle to be adopted. Okay, marginal cost pricing principle is really based on price-taking behavior. That's also called incentive compatibility. Another theorem that's important, the highlight here is the word convex. It's the reverse. If you want to accomplish an efficient allocation, can you actually expect the market to deliver that? The answer is not all the time. At least not without any side payments, transfers. And non-convexity and convexity plays an important role. Now, what does that mean in the context of electricity? So let me just go over here and then to see how this sort of, this is our hypothesis, that you call it. And I will say it's more than a hypothesis because the PJM has discussed this, persuaded enough number of people, including not 100% everyone, but we are deciding to take a move in that direction. I'll give you a sense why we have to take a move. Okay, the reason here is that if you think about what are the three most important things in markets? Number one, actually, obviously, I think once I put up this slide, you will say, yes, price, to get the prices right. And number two, I always will say, as an economist, to get the prices right. And number three, and you know the answer, what else does the market actually do in the wholesale market? It's really to transmit the right prices. And what the prices would do are three things here. Number one is to give the right price signals. Number two is to provide the right incentives. Number three is to provide the money, sufficient revenues. Now, if you fail on any one of these three, the price mechanism is defective. So let's try to measure that. Efficiency here, price reflects the scarcity and cost, number one. And when the demand goes up and the price drops, that doesn't seem that it's doing that function. Number two, it supports efficient system operations. That means that when we give the prices to operators, they should be happy actually to respond to the system operation to keep the lights on. They don't. And once the market is introduced, they try to say that I'm not flexible. You can run it, and I want to self-schedule. I want to actually control my own sort of status. Now, incentive compatibility here is a price-taking behavior here. Incentive compatibility means that you want to actually participate in the market in such a way that you review a true cost. And you cannot optimize the system if you don't know the true cost. So that is an important function of this market. In marginal cost pricing, basically it's presumed that that will happen. But here, we question that. I will show you an example. And reward efficient behavior and entry, that also goes along with all of these incentives. And I think that's a big part of what we do. And revenue sufficiency, it will sustain competitive entry and investment. Although we have attracted a large number of investments so far, so good, but it's done not without capacity market. It was really capacity market was, I generally call it the energy-only market is a beautiful theory, but it doesn't work. And capacity market, it works beautifully in practice, but it doesn't have a theory. So we cannot live without a capacity market. And then the rising revenue in that market, can see that the problem over there, and also the uplift payments. Compared to that, what has happened in this transition in the dynamics is that once the coal and gas are switched, and the price and natural gas price is declining, it hurts two sectors. Coal, obviously, is getting hurt. It also hurts nuclear. Because nuclear in the early days, when they actually got into merchant nuclear, they counted on the high gas prices that give them a very healthy inframarginal rent. And that inframarginal rent is declining. And they actually claim that they cannot survive under the current sort of marginal cost pricing. So in the name of a clean environment, nuclear is actually persuading the states. And then Illinois started a precedent to provide subsidy to nuclear. And the subsidy is a contagious sort of virus. And it actually begets another, it actually suppresses the prices and gets others actually have to get onto that. And sooner or later, that actually vicious cycle will actually kill the market. And that's a concern. And all this, right now, 80% of the new investment in PJMby is from this competitive sector, not from the traditional big companies. And then this balancing actually, and then that the first tier of attack of effect is felt in the capacity market. So there's a lot of debate during the, if you actually close to PJM, you see the debate in the capacity market, and then this energy price formation to get energy prices right. Are really the joint sort of thing at PJM. That's what we see as a problem here, and now actually to persuade everyone to be on board, that's indeed that's very hard. I will explain what we are going to do about that. So for all of that, the evidence of these are all of the impacts of a non-convexity. I think this is a list I'm not going to go through. I think this is more to take the empirical observation and the theoretical prediction and match them, and that seems to have a good match. So non-convexity is a big thing here in terms of reducing the revenue insufficiency, and then also producing right incentives. And so far, we see that overall, the ELMP market is doing okay in providing the right signals in terms of marginal costs. And the commitment cost and other costs are relatively small fraction. If you adjust for commitment cost, the ELMP on average probably will rise about 10%. And the MISO, our neighbor, Midwest ISO, has done that, and they actually, so we are actually not the first one actually to think about this problem. Now, the current pricing mechanism is to use the same model, a dispatch model. I call it allocation model. Okay, that's a market allocation, and the pricing model. They are the same. We don't actually develop two different bifurcated models. And what I'm moving towards here is that in economics, one have to think about these two as separate things and then reconnect them. That's a sort of major sort of departure from the past. And we have very strong support from our internal work and also external experts like Bill Hogan from Harvard, who actually was viewed as the father of LMP. I feel that this is the future. Okay, and I'm not saying that everyone is on board with us, and we are doing a lot of tests, and here I'd like actually you to criticize what we are thinking, whether we got the right problem. Now this is highly simplified sort of way to describe. I hope that this language is precise enough that it resonates with you. That's an appropriate characterization of the problem we face. And the B is a benefit function, D is a demand. Okay, so that is part of the total benefit. If you can carry, now this is a general, very sort of general form. And then the summation here is the cost. I'm sorry. And the cost includes X, which is a continuous variable, and Z is a integer variable. Let's say you can think about this as an investment decision, 0 or 1. You get into the market or you stay out of the market, and that's a discrete decision. I'm not actually capturing all this network, non-convex, other things yet here, but that's further important details. I'm just saying that this is for the purpose of explaining what we are up to, more than addressing the solution here. And the demand supply ought to be equalized. And Y is a parameter. It's, generally, it would be 0. You will see why I put a Y there. It's the excess demand. Now, the current dual optimization of the current LMP is the following. We basically ignore the non-convexity, because after solving that problem, we fix Z at Z naught. Z naught is the optimal, so the mixed integer programming solution. We fix that. Once we fix that, whether it's a 0 or 1, the remaining problem, the restricted problem, is a linear programming problem. It becomes convex. Okay, given that is convex, we can actually find the dual prices for that. And that dual prices is generally known as the marginal cost, called as marginal cost here. And that's very simple, and that's what we do in LMP with the network constraints and so on. Basically, that's marginal cost based. And then I introduced two sort of notations here. Phi on the left side called a consumer surplus, and the pi on the right side is called a producer surplus. Basically, producer surplus is really mathematicians called a conjugate function. And there's some nice features of that concept. Conjugate function has a nice shape. No matter what the C function is, either where the C function is non-convex, but the profit function, the producer surplus function is always convex. And the consumer surplus is a negative of the conjugated function, and is a concave. Okay, these are nice sort of a mathematical structure involved in it, and then we actually can say that we're maximizing the pricing model is to maximize the market surplus is the sum of the two. Okay, this is what the current pricing model. Is that not clear? I hope it is very clear. Now, where do we go from here? Now, using this, the immediate sort of extended LMP is really to convexify all of these to set up a pricing. I said there's a bifurcation between the allocation model and pricing model. The allocation model stays the same model. We still optimize. We still get efficient commitment dispatch and allocation and so forth. But the pricing model is now different. The pricing model here, you know that CH is convex Hall, and you take the convex Hall, CO and conv, of this value function as a function of y, and take the partial, the sub-gradient of this, and then basically you develop a set, and then pick up a number from that. That's the LMP, that's convex Hall pricing, extended LMP. Now that's the concept. Basically, you convexify the problem, and then once the problem is convexified, then you got a shuttle price. That's well defined. Okay, now that's, and then the thing here is that basically the convexified problem is a more relaxed problem. It's a relaxed problem, so when you actually maximize it, you get a greater sort of value out of it. And at the same time, when you pay generators, you pay them And then you will find that somewhere that the market operator will not actually have a balanced budget, and we need to collect the money from somewhere, and that's uplift. Okay, let me leave the uplift question aside. That's in terms of pricing, there are several ways to do it. It's not going to affecting the incentives here, but we can talk about that. Now, but basically, the convex Hall pricing is proven theoretically the one that minimizes the need to use uplift. You cannot do better than that. Okay, and then in theory, you have to come up with some uplift payment anyway in order to get the efficient solution. That's also unknown sort of from the fundamental theorem. This is one way to do it. And whether this is the best way to do it remains, we can debate. So I think a lot of theoretical sort of discussion here is whether this actually meets those three criteria: efficiency, incentives, and revenue sufficiency. At least at this point, it meets the first and third. Is revenue sufficiency? No, okay. The incentives, I will get to that. There's a theorem here. Now, before I get to that, now there are two other ways to implement the expanded LMP. One is a Lagrangian approach. The Lagrangian, it turns out that it's a Lagrangian relaxation instead of convex Hall relaxation. These are two different ways to do relaxation. It turns out that in this problem, they are equivalent. Okay, but the formulation is slightly different. Lagrangian is to use a shadow price P and to formulate this problem directly as a function of P, and using this, it turns out notation-wise they are very similar. The only difference is that there's no convex Hall involved here. You just solve the Lagrangian dual optimization problem, you get a price. Okay, that turns out to be the same. Okay, and another way to do it is that integer relaxation. And integer relaxation is to take the original problem, instead of doing Lagrangian relaxation or convex Hall relaxation, which is after basically conceptually is to convexify the result, the value function. Here is really convexify this digital discrete variables. And Z was a 0-1 variable. In this case, it is treated as if it is continuous. 0-1. It's like a switch. It's a toggle switch, and it turned that into a dimmer switch. And basically, just treat that variable as a continuous variable. And then all of a sudden, that is a convex problem, and you can get a shadow price from this. Now, this generally that the integer relaxation is not performing as well as Lagrangian or convex Hall. But in this sort of simple formulation under the under one condition, it turns out they are equivalent. That condition is that when this cost function is homogeneous of degree 1 in both continuous and discrete variables. Okay, and then in the appendix, and after I finish this, I'll say that is an area of active research, and I think it's very promising over there. And in general, what I want to take away from this is that this is the only one that is practically that can be implemented to get to that, because convex Hall and Lagrangian multiplier approaches computationally they are not really feasible. They are taking too much time. Okay, and then this is one, and then theoretically I'll get to what the PJM is doing. And example one here I want to leave with you is that what difference it makes. Are we really solving a problem not really just for academic sort of intellectual sort of to satisfy our curiosity because Lagrangian dual and the convex Hall pricing is so elegant? Here is a well-known sort of economist, Herbert Scarf. He came up with a problem of the allocation problem. This is a well-known problem of non-convexity. The economists have been struggling, have not really come up with a consensus. And then the problem here is that there are two types of units. Type 1 plant is called smokestack. Basically, that's a more expensive plant. It's larger, but it's fixed cost. Let me see. Yeah, it's basically it's more chunky, and then its variable cost is $30. And type 2, high-tech, is a more efficient plan. But given that this is a discrete problem, okay, and it creates all these non-convexities, and let's show you and what that means. And we solve that for different level of loads. And assume that these loads are fixed. And 6,000, 6,500, and 7,000, this is just a parametric scenario analysis. You get a type 1 unit, sometimes a 2 to 4 and 1 to 7, you know, and then the 7,000 is a perfect 10, because the unit 2 is a 700 megawatt. And it's cheaper units, so you build all of that. You can see that in the non-convexity creates this sort of a random pattern. That's generally expected. And then you get all this output. That is the optimal solution. And we want to implement this solution using the pricing incentives. Good luck. Okay, on the left side, what we see here is that ELMP, you see that is jumping between 30 and 20. Of course, depending on your load and depending on which unit, the marginal cost is either 20 or 30. It depends on which is the marginal unit. And when 30 unit, the type 1 unit is built, that marginal cost is 30. And then, based on those prices, you can clearly see that the marginal cost is not recovering the entire fixed cost. And the question is how much of that is recovered by the LMP, how much of the cost is left to be uncovered. So it's about 40%, 52% on top here is a 50-50. So overall, you roll over, it's about 50-50 or 1/3, and that can be captured by the LMP. And the other sort of significant portion is going to be left out there as missing money or insufficient revenue. Basically, this implies that you have to live with the capacity market, no matter whether you like it or not. And then just imagine that world. This is a very simple insight. You have let's say that all what you have is a very efficient unit, just one type of technology, $20. So that in that case, it's a no-brainer. The marginal cost will stay 20 all the time. And then the fixed cost will be 100% sort of left out. And then you will have the bottom line here, 3268. That will be the answer to that scenario. If we are moving into a world with the supply, the flattening supply curve that we are facing is that. Okay. And then with the extended LMP, you see that basically the extended LMP in this case will basically recover everything under the uniform price. And in this case, you can see that. Okay. And with some sort of marginal lumpiness, very small portion that still need an uplift payment. You can see that the dramatic contrast between these two. Now, people say, now we have, because we don't have price responsive demand, no, we just add a sort of price elastic demand. It doesn't really solve the problem because the demand still crosses the supply curve when you have a step function with a chunk, and sometimes the price still drop to 20. In this case, because only type 2 units will be built when you have price responsive demand. It's more efficient. That's true. Once you have price responsive demand, the results seem to be more efficient. You will never build an inefficient one in this case. But the price will stay at 20, and then you still have a large chunk of money that is left out of the market. So you can see this is a contrast between the left is LMP, the right is ELMP. Okay. So basically, that suggests that we got a problem, and this is non-convexity is a legitimate problem. Now that's a revenue sufficiency story, and then here is another story. It's about incentives. Okay, I think we got 15 minutes, so I probably will not actually go through this, but it's well known in the industry. The LMP creates two sort of a dilemma. Sometimes the units are actually asked to serve, but they lose money, so we have to pay uplift, make whole. That's what we know. And sometimes all those units that are offline, we ask them to stay offline. We want to take you off. They refuse to stay offline. They want to get on. That's why they want to self-schedule. And this type of units, these two things, basically is that when we have a solution that the solution said that the commitment status is 0, but they can make profit. Their pi is greater than 0. then in that case, what do we do? Now that's the current LMP. That is not a problem with extended LMP, but so there is an incentive problem here that creates problems for operations. And then let me say that this is a beautiful example. I like actually to go through. If you ask questions, I will come back to this. But I think I want to leave some time for you to ask questions. This is basically the takeaway is that this is how actually this explains how the generators can manipulate their bidding parameters so that can actually play a prisoner's dilemma game. They actually both lose as a result. Because of the LMP, and so that actually get a price lower than even what we actually predicted theoretically, because they both want to bid inflexibly. When they both do, they both lose. And the key incentive compatibility concepts in economics, there are two. One's called the Bayesian incentive compatibility, the other one called the dominant strategy incentive compatibility. All what that means is that in the dominant strategy incentive compatibility, that means each strategy, the strategy of each trader is very robust, independent of the others. You basically bid your true parameter, you get reward, and your reward is based on your tradable rights of inframarginal rent. You will get your inframarginal rent no matter what you actually being dispatched. Basically, you bid truthfully, that you win. And Bayesian Nash is a weaker form of incentive compatibility. It's based on you need to know the distribution of the rest of the traders, and I will not get there. And then here, what we have is a result. Basically, the known sort of theorem by Hurwitz, who is a Nobel Prize winner on the incentive sort of mechanism, basically saying that with a finite number of traders, no market mechanism can be incentive compatible. And Roberts and Postwith in 1976 established that this is really a classic paper showing that how actually that can be restored when there is an infinite, the number of traders goes to infinity. We basically can show that this property is maintained, and it maintained a very strong form. That is when the number of traders goes to infinity, this market mechanism is dominant strategy incentive compatible. It's a very strong form. Okay. So that's a good thing. And another thing is that the uplift will go down to zero relative to the overall revenue. And tradable right doctrine, because in order to implement this extended LMP, we need a sort of a conceptual framework to persuade the regulator this is the right thing to do. And this tradable right doctrine from economics, basically, this is their right. And the generators, when they participate, they have the right at the price to earn their well-earned inframarginal rent. You cannot take that away from them. Okay, so that is all the basis to provide a justification that this is efficient. Now, I want to actually also say that we are also doing sort of reserve market. Why we bother with that? Okay, this is all sort of a non-convexity. Getting into reserve, two things. I think in many other discussions earlier, reserve is dealing with uncertainty, non-convexity, and enormous. I'll just cut through all of that. Imagine in the future, there is a world, let's say an island in England, or a large island. All the resources are basically solar, wind, and nuclear. All clean, all renewables, all clean power. There's nothing else. And the fossils will also be either ruled out or exhausted and so on. Can we still, I think the question will be, can we still send our crew out there to run the system? Not to mention to run the market, because the price will be zero. Okay? Two things. One is that in that kind of situation, the optimal control will have to depend on the demand side, have to get onto demand side. Now I don't have to describe how to control the demand side. Number two is that the price in that kind of a market is not going to be driven by the energy price. It's the reserve price. And the reserve price equals to the energy price. That equalization is guaranteed. And then in that market, you just say that we're not talking about energy market. Actually, the only meaningful market is demand side reserve market. Here is an example I'm not going to go through. I think I put down all these mathematics so people can check. And what we actually, now this is more like a stochastic context, and when the decision is made, pre-dispatch and load uncertainty resolve the actual dispatch, and then uncertainty about a -1 contingency or other things that affect system reliability. And then there's a theoretical way actually to articulate this reserve as a public good and how it affects reliability in practice. Most of the ISOs are doing this. Three things. One is energy dispatch. One is load shedding. When do you shed load? And the other one, when do you actually violate your reserve requirements? There is a fixed minimum reserve requirement. Sometimes you have to violate it before you shed load. And sometimes you shed load before actually you let go that reserve requirement. So that is the co-optimization question. And these are the pricing principles of co-optimize the energy and reserve. And scarcity pricing takes care of the energy. That means that when the load shedding takes place, the energy price goes to the value of lost load. That's if and only if. And reserve pricing is that reserve pricing is when reserve is actually cut short, then the price is set by the penalty factor that reflects the reliability value. And the option pricing is a relationship between energy and reserve price. The reserve price is always the opportunity cost of not serving energy. But when the marginal cost is zero, then they are equal. That's what I'm talking about. When C equals to zero, the reserve price and energy price are equal. That's on that island that we need actually to do a marginal joint pricing. In this example, and I show that it's interesting. I will skip it. I think the takeaway is that when you do co-optimization, and non-convexity also plays a role here. And even when you actually increase the VOL, then you can get, with the extended LMP, you can see the price of reserve and energy are quite stable, like 60-10, that remains independent of the middle column that shows the scenarios. But it can vary all over the places under the current LMP. Okay, this is a summary, and this is a sort of going back to look at history, how we got here. And today, PJM has received the FERC order to reform its energy and capacity market. And PJM has filed its proposal, and we are waiting for for FERC to tell PJM what to do. And after that, PJM is working with the stakeholders to do this co-optimized energy and reserve market. Right now, there is a deadline by the end of January. If we don't come up with something, then this will be another sort of FERC filing of 206, and then that will actually say that we have to do this. And at that time, so things are still evolving. If PJM is told that, oh, this doesn't make any sense, we can still do no harm. So that's where we are. Thank you.
Yes. Thanks. It's really interesting talk. You mentioned that in PJM, the 60% of generators, they do self-schedule.
Yes.
So I wonder if implicitly means that the generators, they don't ensure that the system, the market design is efficient. Otherwise, if they believe that the market is efficient, they will bid in the market. So I wonder what's the what's the motivation of them to do self-schedule rather than bidding to the market?
That's a good question. I think let me sort of wind back the clock. I think that this is to make sort of complex history simple. At the very beginning in the discussion of this LMP, there was a discussion that the cost structure that reflected in the bids was three parts, and the generators feel that was important to reflect their cost. So the three parts is the energy price, and then there's a fixed cost of startup cost and no-load cost. Okay, and then there is a pricing structure, and the economists don't have a three-part pricing structure. Economists only one part pricing, that marginal cost pricing. And the economists would like actually the bid structure to be collapsed into one part so that it's consistent with the economics and let them do their own bidding, then there will be no self-schedule threat. Now, after the fact that the system operator has a 100 years of traditional practice, they need that information. And this market reform is that you don't want to do any harm and deviate from the current, at that time, current practice. So they give the information to the operator. But feel that a compromise is that uplift was expected to be small. And so the generators would deviate, probably would not be 60% that time, probably will be a small percentage. But 60% was a surprise. And it does tell, and then there are some arguments that the generator technology was more complicated in 3 parts. The CT has multiple sort of configurations and so on. And they say that it does take a longer time than they had real-time market for them, for generator to optimize. Maybe that is there is some efficiency in, gains from self-schedule, given that the market is running every day, every hour. So there's some expectation that they can count on. So it's not going to be too far from the optimal. But no one knows the answer to your question. I'm just saying that there are different views.
But with this ELMP, can we expect that they would wait more to participate in the market rather than?
I think the ELMP, right now, I think the status is that most of these issues that PJM worries about is fast start units. And we don't want fast start units to be self-scheduled. We want actually, it's better for PJM to schedule the fast start units to maintain reliability. So in PJM's filing to FERC, right now actually in the FERC filing, everyone agree that probably capture 80% of the problem, and we would solve that problem and with ELMP, with the integer relaxation. And FERC has not really issued the order yet. That's what PJM proposed. We feel that that's a reasonable thing to do. That's the best we offer. So that solves 80% of the problem. In real world, you never solve 100% problem just because theory says that's the case. Yes.
But yeah, I love the talk. I have a bunch of questions, but just one. So this, Hogan's scarcity price formulation, it looks good on paper, but if you let the control theorists in the room or control engineers in the room, you'd find the value of lost load, the marginal value is 0, because maybe 30%, on any time scales that you care about, hours, you could move it around all over the place. And so, there has to be more of a dialogue, is all I'm saying. I mean, because it can't last. I mean, if you really got demand side in properly, I guess that's all. The value of lost load is.
I think you touched on a question. I think we're still in active discussion with Bill Hogan. I think.
What would you say to that? I mean,
I think that right now, in the reserve market, we actually are facing this problem right now. The situation is the ERCOT, the Texas model. They use the value of load concept, and $9,000.
Yes.
Okay, that's the value of lost load. But they don't have a co-optimized energy and reserve market. But PJM situation is different. We have a co-optimized energy and reserve market. We don't necessarily have to go through that route because in ERCOT's model, their presumption is that they will maintain their minimum reserve requirements, the N-1 contingency requirements before and the shared load first. So they cut through that VOL part first. And then the value of reserve is the VOL minus the system marginal cost. It's a dynamic sort of demand curve. The operating reserve demand function is a dynamic. That's the ERCOT's construct. And PJM is like actually more nuanced. PJM doesn't have VOL at this point. Has a maximum offer price that FERC approved, $2,000. Has a maximum ELMP, $1,000. That actually is not going to, it's going to be raised to $2,000 at least. But the PJM is that the procedure, the operating procedure is that they would not really want to share load just for the sake of preserving the MRR. Believe that the reliability value here warrants that we can cut down the reserve first and then try to use other measures to recommit a lot of units quickly to recover that in 15 minutes So that is our procedure. In that case, the reserve, the penalty factor is more relevant. So our penalty factor at this point is 850. So if you add 850, and then there is a spinning and also non-spinning reserve, you can get up to the reserve price to 1,700. 1,700 plus 2,000, the highest price will be today, will be 3,700. And so implicitly, the current VOL is higher than the value of loss load is higher than 3,700. But PJM is not prepared to name a value of loss load explicitly. Okay, so I think here is the mentality here is that in terms of price formation, we're changing the price, we're not changing the operation. Now, we don't want to let the tail of the dog to wag the dog. The operation is robust, and there is, if you look at philosophically, the NERC standards, National Electric Reliability Council standards, and the economic principles are not really internally consistent. So if to forge consistency is a foolish errand here. So we basically try to translate as best we can, and then use a bifurcation of this allocation model and pricing model underlying the ELMP approach, and then try to basically to preserve that consistency, and hope through competition this will become really we solve the major part of the problem. So, I think this is a fascinating sort of issue. I don't have all full answers. I'd like actually to use this opportunity, and if you have any sort of insights, and I will be happy to discuss with you. Nothing, I think I'm describing this. I think all of these things is that before FERC has issued an order, FERC is certainly reaching out to get all of the best ideas, and PJM is also open. So we're not really saying that until it happens, it hasn't happened. Now these are all sort of in the process of discussion.
It seems that you have three criteria for prices that cannot be met by the current LNP formulation. When you do this relaxation, do you sacrifice the efficiency?
No. You can see that answer is definitively no. Because to the extent that we get the same information and we use exactly the same allocation model, the allocation model assures efficiency. We're not compromising that. And the pricing model is supporting the efficient solution with incentives and with adequate revenue. The revenue adequacy basically is, in economic jargon, is called individual rationality. And then the incentive here is produce the right incentive for entry and so on. Those are important economic concepts that have not really been viewed actually as put in the center stage until now, given that the debate, what happened is that when this, the thing is that competitive market creates a big field transition, and then external policy and the politics and the environment create this, all this policy debate that affects the capacity market. And that makes all these, that distorts incentives, and that makes this incentive issue and the revenue adequacy issue at the center here. Then we need to address all three at the same time. And the best shot we have on the table is the extended LMP.
Relaxation from 0, 1 to something in the middle, does that affect the optimality maybe?
No. That's very important. We no longer have to actually attach the base point in the pricing model. We can throw away the dispatch in the pricing model. Allocation is irrelevant. We don't even want the operator to see that. Only you get the prices from the operating model, and then from the current SCAD model, we no longer actually look at the LMP. Basically, that is thrown away.
I didn't quite understand. So I understand that your magic ELMP eliminates the need for uplift, but would it also move people from the capacity market back to the energy market?
Yes.
So you will not need the capacity market?
I will not say that you will not need.
Well, it will minimize the need.
Yes, it will be minimized. I think, yes. I think basically there's no reason to close the capacity market. We don't need to close it. The dependence on capacity revenue will be reduced a lot. Okay. Oh, they are.
In the scarcity pricing formula, the uncertainty window over which you're defining this expectation, does it have to be related to the response time of the operating reserve product? So, for example, I think in Texas, response times for operating reserve are 15 minutes, but the uncertainty is calibrated over a half-hour look ahead, or maybe it's half-hour and one hour. I was curious as to, if what you're trying to remunerate is operating reserve with a response time of a half hour, does that bell curve that you use to compute the demand function need to be the half-hour uncertainty bell curve, or can it be deeper, which would address, I guess, the first question to some extent?
That's a very good question. We have a discussion. Let me give you a quick answer. I'll be happy to discuss with you offline, and there's a lot of things going on. Yes, we actually draw from ERCOT's experience, and we actually consider that the use of 30 minutes look ahead for this spinning reserve, and 1 hour look ahead of a 30 minutes operating reserve, and for the reasons you described. Now there is a forecast error, and also we need basically at least 10 minutes to run the schedule to commit the unit, so we have to use the information available 30 minutes before the target time. And this is in stochastic programming, this is well known as action delay, information delay, and that's, yep. Okay, with that, I will be around for the whole week, so I'm not disappearing. So if I open up your questions, I'm all for it. Thank you.